Okay, this is the November 2018 Paper 1 Physics Multiple Choice Questions, Past Paper Questions, Matric Physics. Okay, the first question is about inertia. Inertia is the tendency of an object. If you go back to the grade 11 guidelines, there are two definitions that this question is closely linked to: Newton's first law of motion and define inertia. Define inertia as the resistance of an object to any change in its state of motion. So let's think about what this means. What is your state of motion? You can either be at rest, okay? You can be moving at a constant velocity, okay? Or you can be accelerating or decelerating. These are your options for your state of motion. And if you have inertia, it depends on your mass, how many particles you have. And the more particles you have, the less likely you are to change your state of motion if a force acts on you. So in the memo, it gives you the answers, both C and D. Inertia is the tendency of a body to remain at rest or in a state of uniform motion. This is true. A body will not want to change its state of motion because of inertia. If you're sitting still, you'll stay sitting still. If you're moving, you will keep moving. However, also the same applies whether a force is applied or is not applied, okay? So both of these are correct because inertia says an object resists changing its state of motion. So if you resist changing your state of motion, you will remain at rest or you will remain in your state of uniform motion. This is a resistance to a change. Also, trying to maintain your velocity when a force is acting on you is a resistance to a change in state of motion. So both C and D are correct. The question was poorly phrased in terms of what is inertia. It is a resistance to change in motion. So you can resist remaining at rest, you can resist a state of uniform motion, and you will want to maintain your velocity when a force acts on you. So both C and D are correct because a body does not want to change its state of motion. Now, this is a lift issue. Explaining lift issues is tricky, okay? What do you need to know? The scale reads your normal force, okay? The only time the scale does not read your weight is when the lift is accelerating. So if the lift is accelerating, and it can be accelerating either positively or negatively, i.e. going up or going down or slowing down or speeding up. If a lift is accelerating, then your weight changes. Your weight according to the scale, okay? Your weight's not going to change, but your weight on the scale, the reading on the scale changes. So if we are at a constant velocity, okay, at a constant velocity, your weight will be what you are expecting it to be. The scale is the normal, okay? The scale has your normal weight, not your normal force weight, but your normal weight, what you're expecting it to read. So in here, we can remove immediately A and B because they both say constant speed. So if you've got constant speed, you are going to not have a change in the scale reading. It won't be the maximum. When is the reading on the scale largest? Now think about this. There's a whole long complicated explanation. Here, if we are accelerating with the applied force from the lift upwards, okay, is the net force upwards, okay, or are you accelerating downwards, okay, if the net force from the lift is downwards? And then you take into consideration your weight and the acceleration due to gravity. You are going to find that the answer is C. So I always say, if you're answering these questions and it's not too complicated, think about when you get in the lift. When do you get in the lift and feel heaviest, okay? You feel heaviest when the lift starts going up, okay? And you feel lightest when the lift is like falling away under your feet. Okay, if you think about that. So when do you feel heaviest? When the lift is either accelerating upwards or sometimes when it is stopping, okay? But if you are going downwards faster, the lift falls away from your feet, you feel lighter. So I don't want to draw all the vector diagrams because I don't explain this 100%, but I just say, think about when you get in the lift. When do you feel heavy? When do you feel light? You feel heavy when the lift is pushing up on your feet because you are accelerating to go upwards. And when do you feel light? When the lift is falling away from your feet because you are going faster, going downwards. So it depends on where is the net force. Is the net force from the lift upwards or is the net force from the lift downwards? But you will feel heavy, which is when there's a big reading on the scale when the lift is moving upwards at an increasing speed. Okay, in 1.3, an object is projected vertically upwards. So if this is the ground, here will be my object going upwards. As the object rises, its velocity and acceleration are both directed upwards. No, where is acceleration? If we are ignoring air resistance, the object is a projectile and the acceleration is g, which is 9.8 meters per second, and it is always downwards to the center of the Earth due to the law of universal gravitation. Its velocity and acceleration are both directed downwards. No, that is not true. The v is positive and the a is negative. So the answer here is C. The velocity is up, but the acceleration is down. Remember, the acceleration for a projectile is always down to the center of the Earth. Okay, ball P and ball Q of the same mass are dropped onto a concrete floor. Both balls hit the concrete floor at the same speed. Ball P rebounds with the same vertical speed, but ball Q rebounds with a speed a half v. Refer to the diagram below. Ignore air resistance. Which one of the following statements regarding the collision of each ball with the floor is correct? Kinetic energy is conserved for both balls P and Q. No, this is wrong because EK equals a half mv squared, and for this ball here the kinetic energy has decreased. For this one the EK is the same. Okay, so this is not true. The change in momentum of ball P is greater than that of ball Q. This is in fact the correct answer, and I'll show you why in a moment. Let's rule out this one. The contact time with the floor is the same for both balls P and Q. There is not enough information in the question to make that statement. Why is D wrong? Momentum is conserved for the collision of ball P, but not for that of ball Q. Let's just think about this. At first glance, this one looks correct, but you've got to remember momentum is a vector, okay? And the vector is given by the sign of the velocity. So if we think about ball P, its momentum before the collision is plus P, which is equal to mv. If we say like down is positive, okay? And then after the collision, its momentum is minus P. So is plus 1 the same as minus 1? Are they equal? No, they are not. So we cannot say the momentum is the same because the momentum has changed its sign. But I do agree D looks quite correct. However, if we look at B, it is the most correct, okay? Because what is the change in momentum? Delta P equals, the mass is the same, Vf minus Vi. So if we look at ball P, okay, the mass is going to stay the same. We have to consider vectors here. So if we say, what are we saying? Are we saying up is positive or down is positive? Let's say down is positive. Okay. So if down is positive, after the collision, my final velocity will be minus V minus positive V, which is what it was in the beginning. So I have minus V, because a minus and a plus make a minus. So I have M minus 2V, and that is for ball P. if I look at ball Q and I do the same thing, the change in momentum is the mass, Vf minus Vi. We use the same convention, sign convention. The final velocity is upwards, so we said down is positive. It's minus a half V minus plus V. So I end up with m minus a half minus 1v, which comes to m minus 1.5 v, because minus a half minus 1 gives you minus 1.5. So this one is greater than that one. So the change in momentum of ball P is greater than that of ball Q. This is the correct answer. And you just have to consider the vector nature of momentum to rule that one out. Okay. 1.5, if the net work done on a moving object is positive, well, let's think, what formula do we have for net work? Net work equals delta EK, which is a half mvf squared minus vi squared. So if this gives you a positive number, it must mean vf is big and this is small. That is how we will get this to increase. So if the net work done on a moving object is positive, the kinetic energy of the object has increased. Yes, it just works out that way. The spectrum produced by a moving asteroid as observed from Earth indicates that the light has shifted towards the blue end of the spectrum. Remember the spectrum? Red, orange, yellow, green, blue, indigo, violet. And we usually say the thing is either red shifted or blue shifted. So when we look at this, this is a high frequency. This is a low frequency. And so this means if you are a low frequency, you have a long wavelength, and this one has a short wavelength. Okay, so if we are blue shifted, if we've gone this way, then the frequency has increased. Okay, a blue shift shows that the frequency has increased because blue has a higher frequency than red. So if we are blue shifted, how do you increase frequency? Something must be moving towards you. So if this is the Earth and this is the asteroid, how do you get it to have a smaller distance? It must decrease. So my answer is either going to be A or C. But what has happened to the frequency of light? If we are blue shifted, the frequency has increased. So my answer here is going to be A. Blue light has a higher frequency than red light. It's a blue shift, and that means the object is moving closer towards you if you have a higher frequency. Then we go to 1.7, and here we can use my favorite saying, like charges repel, the thing you must learn by heart, and then unlike charges attract. This is the rule to answer this question. We've got three charged spheres, X, Y, and Z, supported by alternating threads of equal length hang from a beam. Sphere X is negative. Sphere X attracts. Sphere Y but repels sphere Z. This immediately tells me that Z is negative. If Y is attracted, according to the laws, Y can be attracted if it's neutral or if it is positive. So you need to check the answers. Sometimes they're going to put neutral in, sometimes they're going to put positive. But we need to find the answer that says Y is either neutral or positive and Z is negative. And this one here is the answer A. Always remember, like charges repel. Okay, this question here is taking your knowledge from grade 10 because it says the cells have negligible internal resistances. It says the cells and resistors are identical. Now they want you to talk about the power dissipated in resistor X is P, the power dissipated in resistor Y is what? To answer this question, we have to think about these circuits. We know if we're talking about power, we can use any of the formulas, I squared R, or power equals V squared over R. So before we go and look at the numerical value, let's have a quick think about what would actually happen. In this circuit here, if we've got all of the identical resistors and cells, okay, here the total resistance for this circuit is large, okay, because the resistors are in series and current is inversely proportional to resistance, so this will have a small current, okay. We also know that a series circuit is a potential divider, so this resistor X is also going to have a small voltage across it. In this nice parallel circuit here, this one is going to have a large current because a circuit is a potential divider. A parallel circuit is a current divider. Okay, so the current is going to be larger, and also the voltage is going to be larger because in a parallel circuit, if we put a voltmeter over here, it would read exactly the same as all of these voltmeters, okay, everywhere on this circuit. So if you check here at the formula, if I increases and if V increases, the power increases. So in my answers here, this is resistor Y. This one, it has to be one of the bigger answers, okay? You can't be giving me the answer A or B because in this second parallel circuit on the right, both the current is larger and the voltage is larger, so the power has to be larger. But have a look at the formula. Both of the formulas have a squared factor on it, okay? So if we think about this one, if this voltmeter has got a voltage V, then what would be the voltmeter over here and the voltmeter over here? It would be a half V because a series circuit is a potential divider. So if I have a half squared, it is giving me 1 over 4. It is a factor of 4. This one will have a quarter of what is this, V? A quarter V squared. This one will have V squared. So if we look at mathematically, this one is 4 times bigger. So the power is going to be 4 times greater. The same thing will happen here. This current, the current will be larger because the total resistance of this circuit is smaller, okay? So the current is larger, but the answer is 4P because of the squared factor in power equals I squared R. So let's look at now 1.9. Where's my mouse gone? Where's my mouse gone? Here's my mouse. Let's look at 1.9. Which one of the following actions will not cause an increase in the induced EMF in a coil if the coil is rotated in a uniform magnetic field? Well, how do we increase the EMF? So remember, we can change the windings in the coil. Remember, we've got this formula E equals minus N delta phi over T. So rotating the coil faster will increase the EMF. Increasing the strength of the magnetic field, that will increase the EMF. Increase the number of turns in the coil, that will increase the EMF. Replacing the coil with a coil of lower resistance, this one will do nothing because it's nowhere in the formula does it discuss the resistance of the coil. It only is the windings of the coil, the strength of the magnets, how fast you turn it. So that one will not be considered. A learner writes the following statements about the emission spectrum of light in a notebook. An emission spectrum is formed when certain frequencies of electromagnetic radiation pass through a cold gas. No, if you are cold, you absorb energy, so this creates an absorption spectrum. This is wrong. The lines in the emission spectrum of an atom have the same frequency as the corresponding lines in the atom's absorption spectrum. This is true because remember, in the Bohr theory of the atom, we have electrons at fixed energy levels. And what is causing the emission and the absorption? It's when electrons jump between the different energy levels. And so they will have the same frequency because remember, E equals HF. So the energy is given by how far they jump in the atom. Okay. An emission spectrum is when the atom makes transitions from a high energy to a low energy. Yes, this is correct. So the two correct answers are 2 and 3. Remember, cold things absorb energy and hot things release energy, emit. Releasing, emitting. Absorbing, sucking it all in.